All right, so we're going to start probability. So this is section 11.1, and in section 11.1, why do none of the markers like me anymore? In section 11.1, we're going to talk about the idea of what, that one's even better. We're going to talk about what the idea of probability is, okay? And so we're only going to do section 11.1 today. I know on our calendar it says we're going to do 11.1 and 11.2, but I want to take our time going through section 11.1 because calculating probability is essential for all of the other sections in this unit. Okay, so we've got 8 sections that we're going to go through. We're going to use probability in different ways. So it's super important that we can calculate it very well. So the first thing that I will tell you is just define a little bit of terms. Okay, and the word experiment. An experiment, I mean, it's kind of hard to define what an experiment is. An experiment is an operation that produces results. Sometimes we call those results data. Okay, so there's 2 types of probability, and the first type of probability is based on experiments. And so what we have is in our experiments, we have what's called outcomes. Okay, the outcomes are the possible results. So the outcomes are the possible results of an experiment. And so then one more term for you, an event. We talk about an event, which we will talk about events a lot when we're dealing with probability. An event is some subset, if you remember that word from our first unit, an event is some subset of the possible outcomes. So for instance, just to put something tangible to this, now we will deal with some simple types of experiments in here as you are learning how to use probability and discuss the lingo. But again, this is something that is super common. So being able to understand that probability will help you in so many ways when you're reading things about any sort of data. I mean, if you've looked at all the COVID stuff, all the graphs, all the probabilities, everything based on that is all probability. So being able to understand that. So for instance, a nice, simple experiment is I'm going to roll a die. Okay. Die is singular for dice. In case you don't know, I'm not wishing anybody harm here. So we're going to roll a die. So how many sides are on a die? There are 6. Okay, so the outcomes of rolling a die, okay, are the numbers 1, 2, 3, 4, 5, 6. The outcomes are kind of like the universe when we were dealing with sets, if you remember that back in the day. So I can talk about any number of events now that I know the outcomes. So I'm just going to label these events with a letter so that you can distinguish them from all the possible outcomes. So we could talk about event A. Event A is I want to roll an odd number, so a 1, 2, or a 3. Event B would be something like, hey, I'm just interested in rolling a 6. Okay, or any other subset. I'm not going to bore you to death by listing a whole bunch of subsets. Okay, so the experiment is I'm rolling a die. There are 6 sides, so my possible outcomes are 1 through 6. And so an event, I've listed 2 events. You could list other ones. All right. I think I said I could roll an odd, and then I wrote down 1, 2, and 3. Good job. Good job, Berkster. 1, 3, and 5. Not that 1, 2, and 3 was a bad event. It just wasn't what I said. So there we go. Yes, I'm out of it today. Here's what happened today. I'm recording this, so good for me. My daughter, who now is at college, she has a cat. His name's Olson. And he's usually a very lovable little guy, except in the morning when he's hungry. And today he decided was the day he's gonna start walking on my throat. Okay, so I'm trying to sleep and I got a cat and I don't want to enable him, right? I'm not gonna feed him earlier and earlier, then he'll wanna eat at like 2 in the morning. So I'm throwing him off the bed. He keeps hopping up, throwing on my throat. So I woke up kind of in a weird state today. So I apologize, and I apologize for you watching this on video in future semesters that you had to hear that story. So there you go. All right, so all that to say, yes, you know more about me now than you ever wanted to, and I apologize for that. All right, so the first type of probability, there's 2 types that we're going to talk about. The first type of probability is called empirical probability. Yeah, you don't need a stats calculator or anything. A plain old, in all honesty, a plain old 4-function calculator will get you through, but if you have a science calculator, if you borrow one of mine, anything like that will be fine. If you take stats, I think most of the stats teachers at Polk State will actually use a graphing calculator because it has some ability to, you can put data in and it'll remember it, and that's helpful. If you go that route, that will be the calculator you'll probably use. But here I brought my handy dandy little science calculator. So empirical probability. Empirical probability, the word empirical means that this is probability, not probability. Oh my goodness, I should just cancel class. Probability based on an experiment. So empirical probability is probability based on an experiment's results. Okay, so you've actually done something and you're looking at those results. And so when you calculate empirical probability, what you're calculating is the probability of the next event. Okay, so empirical probability is the probability of the next event. And so here's a little notation about probability. Our book, and in this class, we'll use for the most part the letter P for probability. And then in some parentheses, we will describe the event. And here's how you calculate empirical probability. Okay, so the way you calculate this is in the numerator, you're going to put the number of times your event happened. And then in the denominator, you're going to put the total number of trials of the experiment. That's a lot of words for something that's actually pretty simple to go ahead and calculate. Okay, so for instance, y'all don't have books. I probably should have typed this out. So once again, I'm winning this morning. All right, so I'm just gonna real quick on the board, write down some experimental results. So this is just an example that I'm reading from the book. Okay, so it says at a Little League concession stand, the last 40 purchases were as follows. So we have 40 purchases, and here is the breakdown. The breakdown is that 16 people bought water, 14 people bought Gatorade, and 10 people bought soda. Okay, so that's the data. Okay, so the experiment that is performed is I've just been watching off to the side what people buy. These are the results. So here's what I want to know. What's the probability that the next person, because that's what empirical probability tells us, what's the probability the next person buys water? So what is the probability that the next person that comes up to the window at the counter purchases water? Okay, well, here we go. In the numerator, it's the number of times that my event has already occurred. So how many times have people already bought water? Okay, 16. How many total times have I observed people purchasing anything? How many times has the experiment happened? 40. 40. There you go. So probability is the ratio of basically successes. How many successes have I observed divided by total? Okay, probability is the ratio of successes to total. Now, there's two ways that you'll write probability, so make sure when you're going through in My Math Lab and you're doing your homework that you are reading carefully what they want. Okay, the two common ways to write probability is either you reduce the fraction or you write it as a decimal, usually rounded to 3 decimal places. Okay, so 16 over 40, 8 is going to go into both of those. 8 goes into 16 2 times. 8 goes into 45 times. So that is a good probability. What this tells me is the general rate here is 2 successes or 2 waters for every 5 purchases. That's the probability that's going on here. Or, okay, I don't care on the test, I don't care which you use. Okay, I will say in the instructions, either give me a reduced fraction, or if you give me a decimal, make sure you round it to 3rd decimal place. Okay, that gives us enough. Detail. This one's a terminating decimal. If you go into your calculator, 2 divided by 5 is 0.4. Sometimes you'll see probabilities given as percents. That's also something legitimate. So 0.4 is 40%. 40% of the time you're going to get. So when you're reading the weather, okay, and you're looking on your weather app and it says, if it says there's a 50% chance of rain, that's an empirical probability based on whatever the conditions are. It's telling you on this day, based on past results, there's a 50% chance of rain. So that's some place that you deal with probability. So according to this, here's a nice relaxing problem that I want you to do. What's the probability the next person, given that data, buys Gatorade? Okay, so for this problem, what's the probability that somebody purchased Gatorade or the next person purchased Gatorade? So how many successes, how many times does this event happen? 14. 14 out of how many times? Great job, thank you very much. So I can reduce this. If you wrote this as a reduced fraction, 2 goes into the top and the bottom, 2 goes into 14 7 times, 2 goes into 40 20 times. Or if you wrote this as a decimal, when you have to round, you round to the third digit, but this one again is going to go ahead and terminate. So 0.35, I think, if I did my division while I was talking, which is always suspect. We doing okay so far? Empirical probability means you have actually performed an experiment. There is data that you are basing this off of. Here's just another example I've summarized for us. 500 people were given a medication. Okay, so we're trying to see if this medication is effective. Again, this is super simple. We're not talking about sample sizes and things like that. That's what you do to get the statistics. You'll see what the appropriate sample size is to have confidence in these results. We're just simply talking about the probability right now. So 500 people are given a medication. For 379 of them, there was a reduction in blood pressure. For 62, there was no change. And then for 59, there was an increase. So here's what I would like you to do. You're going to do 2 things for me. Round both of these. Well, I guess I would recommend giving this as a decimal, but you're welcome to do what you want. I want to know for the next person that takes this drug, what's the probability that their blood pressure is reduced? And then what's the probability that their blood pressure will be increased? Yep, that would be my suggestion for you. Okay, so for the first problem, given this data, this experiment that's going on, if you're the next person and that takes this drug, we want to know what's going to happen to you based on this. So what's the probability that's reduced? So first, in the numerator, what number am I going to put in the numerator of this? Okay, that is the number of times this event has happened. Out of how many times? 500. And when you give a decimal, what is that? 76?
Do we do 3 decimals?
Yes, you should do 3. 758. See, the reason why is when more accuracy is available, we want to have the more accuracy. If we round here to the second decimal place, okay, that makes this look significantly different. 0.76 and 0.758 are significantly enough different that we want to make sure that we avoid round off error, things like that. In fact, some books want you to do 4 decimal places per probability so that you get even a little bit more accuracy. So yeah, we don't want to round too soon, especially if you're going to use a number. If you use 0.76, like we saw this with pi in the last unit, when we used 3.14 versus 3.1415, you're getting different answers. And so it makes a difference. Okay, so what's the probability it's increased? What's the numerator going to be in this situation? 59, great. What's the denominator going to be? The number of times my event occurs was 59. Total number of times the experiment was performed is 500. And when I do that, is that 0.118? Great. So far, we so good? You do that math in your head? Sort of, yes. Yes. But I'm cheating because this is the thousandth place. So if I multiply 500 by 2, that's thousandths. So what I did is I multiplied 59 by 2 because that's a small enough number that I could do it. So there you go.
That's
Okay.
I wouldn't think to do that.
Well, that just comes from understanding. And so if you take MGF 1107, we talk about the decimal system and place values, and we'll have a great time doing it. Yeah, I'm not super good with doing arithmetic in my head. That's fun and it's good at parties to impress people, but it's not always super useful. Okay, so here we go. The next thing is we are going to move from empirical probability to something called theoretical probability. I'm pretty sure I spelled theoretical wrong there. If I haven't spelled it wrong, theoretical. Yes. Good, I'm glad I'm recording today. Theoretical probability. So sometimes we want to know what should happen, and even if we don't do the experiment. So the theoretical probability, the probability of an event, is when you're thinking through the things that could happen, like when you're flipping a coin or rolling a die or other situations that we will encounter. The numerator, it's very similar, okay, kind of the verbiage is a little different. The numerator is the number of elements in event E. Remember, event E is a subset of every possible thing that can happen. And in the denominator is the total number of possible outcomes. Or another way to say that is the total number of outcomes in your event. So there is a relationship between the theoretical and the empirical, and this is something that when you take statistics, again, that all of statistics is based on. So I'm going to share with you this picture that we have in our book. So I'm assuming somebody at some point did this. So here's what I want to show you. Okay. So we're flipping a coin. Okay, when you flip a coin, how many outcomes are there when you flip a coin? 2.
Okay, we usually call them heads or tails. It just depends on what's on the front and what's on the back. So there's two possible things that can happen. Okay, so if we perform the experiment though, if I toss the coin 10 times, okay, if the world was perfect, half the time you're going to get the heads and half the time you're going to get the tails, right? It's 50-50, 5 and 5. But we know that's not what happens. If I gave everybody a quarter and we flipped it 10 times, different things would happen. So whoever performed this experiment, they actually got 4. Now here's the thing. Here's what I want you to notice. This is only one different than what you would hope for, right? This is only one different than 50-50, right? 50-50 would be if you got 5 heads, you get 4. So it's only one different, but because I've only flipped the coin 10 times, that one difference is significant, right? It's 1 time out of 10. It's 10%. Okay, so missing the mark by 1 time leads to a empirical probability of 4 times I flipped ahead out of 10. That's 40%. So now what happens is I'm going to, because I'm bored, apparently it must be raining outside, I'm going to flip the coin 100 times. Well, again, if you're 50-50, if you're spot on, you would expect to get 50 out of 100 times you would get the heads side of the coin. So whoever performed this experiment, though, again, because not everything happens the way that you theoretically should, you get 45. Now notice this. Now we're 5 different than we would expect. In the previous line, we're only 1 different than we would expect. Now we're 5 different, but because I've flipped the coin 100 times, right? I'm 10 times more flips than the previous one. Those 5 have less significance. So 45 out of 100 is 0.45. Notice the probability, the experimental probability went up from 0.4 to 0.45. And we could keep doing this. I'm not going to bore you more than I have to and go through the whole chart. But, okay, so apparently maybe you got punished for doing something wrong and you decide to flip the coin 100,000 times. Okay, that would be quite the way to spend the weekend. 50-50, probably done with a computer, but that's okay. 50-50 would be 50,000 times. Notice this. What actually occurred in the experiment was 49,770 heads. So this time you've missed it by 230. So that seems like a lot more, right? The first time we only missed it by 1. The second time we missed it by 5. This time we miss it by 230. But again, here's the thing that I'm trying to implore upon you. 230 out of 100,000 is a lot less significant than one missing it once out of 10 up here at the top. And you can see that every time it oscillates a little bit. Every time you flip the coin more and more, you get closer and closer and closer to what you would expect, which is a probability, what you said at the beginning. There's 2 possible things that can happen. And so I would expect to get a heads when I flip my coin half the time, or 0.5. So what this is called, let me change back my camera. So if you're really fascinated and you're watching the video, push pause right now.
Called is the law of large numbers. And all of probability, all of statistics is based on this idea of the law of large numbers. Doesn't make sense or it doesn't give you accuracy to talk about experiments that haven't been performed a lot of times. It's kind of the problem with a lot of if you're familiar with computer projections, the computer projections for COVID, the computer projections for things like climate change, if you study this stuff, you notice the computer projections are wildly inaccurate because there's such a limited, small amount of sample size for these things. It's hard to make accurate projections. You need a lot of data. So the law of large numbers says that as the number of times an experiment is performed increases, okay, so as the number of times that an experiment performed increases, the empirical probability that's closer to the theoretical. Meaning your results get more accurate. Basically, if you want to just summarize what I just wrote, used a lot of words to say, as your number of trials increases, your results get more accurate. Your results are better to make predictions. And that's the usefulness of probability. So what we're just going to do for the next 40 minutes or so of our time is I just want to make sure that we get really good at calculating probability and we're comfortable with it. Because when we come back next time, we're going to talk about other things that are based on probability. This is the foundation for the whole section or this whole unit is being able to calculate probability. So for instance, let's start with something that's nice, simple. I already mentioned this. So what we're going to do is we're going to roll a die. Not just yet. Okay, not just yet. There's going to be a couple, but not anywhere near what you had to memorize in the previous section where we had those two sections on volume and area, things like that. So this is less formula intensive, but please practice. Okay, this is super important. Okay, so we're going to roll a die. That is the experiment that we're going to do. We're going to consider theoretically. So here's what I want to know first. What's the probability that I roll a 6? What's the probability that I roll a 6? Okay, so remember, probability is successes divided by total. The number of times that I should get a 6 divided by the total number of things that can possibly happen. So when I roll a die, how many sides are labeled with a 6? One. Out of how many possible outcomes are there when I roll a die? 6. I'm going to leave it there. That's a nice reduced fraction. Okay, but we know, again, this is what theoretically should happen. But if you sit there with a die, you roll it and you record what you get, well, it's not always going to be perfectly 1 out of 6. As you roll it more and more and more times, if you want to spend this week doing this experiment, it'll get closer and closer and closer to 1 out of 6. Okay, try this one. I want you to find the probability of rolling an odd number. All right, when I roll my die, how many odd numbers are there? 3. The 1, the 3, the 5. I made that mistake earlier. The 1, the 3, and the 5. There are 3 possible odd numbers out of how many? 6. Okay, so I'm going to reduce this. 3 goes into both of those. So half the time you should get an odd number. Excellent. Try this next one. Read carefully. I do have a purpose with each of these examples. Those examples are just getting comfortable with probability. This next one is comprehension. What's the probability that I roll something less than 3? What does the word less than mean? Means not including 3. Yes. If I want to include 3, I would say less than or equal to 3. Yes.
I have a question.
Sure, bring it on.
This applies to math, or does it apply to other stuff? Sometimes I can do the test and we don't include the less than or equal to, like, I don't know, let's say I'm on the science test, they say less than, but for some reason I get it wrong just because I'm supposed to include that plus anything that's less than that.
Well, we saw back in the sets, when we saw problems, we could say the word inclusive. Okay, so we would say when we had our universe, let's say the universe was the numbers 1 to 50, and I said, I think one of the questions was, give me the set of numbers between 5 and 10 inclusive. The word inclusive means to include the ends. But if you just say less than does not include the end point. So either you're misremembering the verbiage or the person who's asking the question is mischaracterizing. So one of those two things, but less than means I'm not going to include. Okay, so you can take that to the bank in here. Okay, that's not going to change in here at all. So less than 3. What are the outcomes that are less than 3? They are what? 1 and 2. Okay, so there are 2 outcomes, 1 and 2 out of 6. So again, I'm just going to reduce. If you give me a decimal, make sure you round appropriately to at least the 3rd or 4th decimal place. And then when I reduce this, it's 1 out of 3. Every 1 out of 3 times, I expect to get a number that's less than 3. We doing okay so far? Nice, simple, relaxing example. We're going to work up in complexity from here. Yes.
If there's not another, like, say there's only like 2 digits on your decimal, you just leave it there, you add a 0.
Oh, you just leave it there. Yeah, you don't have to worry about. When you take a science class, you'll talk about something called what is it called? Significant figures. Okay, so there is time in science where you would put the 0 to show that I've actually measured to the 3rd decimal place. But we're not going to go deep into significant figures here, so you don't have to worry about it. So anyway, all of that was, I was just trying to impress you with knowledge. Okay, here we go. The probability of a 7. Okay, when I roll my die, my 6-sided die, and we're not talking about any of the Dungeons and Dragons dice, anything like that. It's just our normal Yahtzee dice. Okay, I'm rolling one of those. What's the probability to get a 7? Oh, there you go. How many 7s are there on my die? There's not one, right? Out of 6. So that, I can't get a 7. Okay, so if you're counting on that, when you're playing Monopoly, when you have to roll one die, it's not going to happen. I've got one more, and then I'm gonna tell you why I'm asking some of these questions. The last one is, what's the probability that I roll something less than 7? So how many outcomes, when I roll my die, how many outcomes are less than 7?
All of them.
All 6, right? 1, 2, 3, 4, 5, 6. So 6 out of, I've got 6 possibilities. And so that is 1. So let me tell you why I asked those last couple questions. It wasn't just to be obtuse on you here. The first thing, this is probability trivia. Stuff to know. The probability of something that's impossible is 0. If something cannot happen, its probability is 0. Okay, so the probability So the first bit of probability trivia, there's 4 bits of probability trivia. The probability of an event that cannot occur is 0. Well, then the flip side of that, and we've already seen it, what's the probability of something that has to happen? 1, yes. Because we said, what's the probability of rolling something less than 7? Well, that event occurs, that event accounts for everything. So the probability of an event that is certain to happen is 1.
How much harder is the problem to do?
Okay, modestly harder. Okay, so all probability, here's probability trivia 3, the probability of any event then. So any answer you give me on the test, on the homework, if I ask you what the probability of something is, Okay, all probability has to be bigger than or equal to 0, because the smallest value you can have is 0. That's the probability of something that's not going to happen. So what this tells me is if you get a negative answer for probability, you've done something wrong. Okay, there's no negatives. And then the biggest probability is going to be 1. So if you get a probability of 2.7, again, you've done something wrong. Okay, all probabilities will be between 0 and 1. Then the last bit of probability trivia, I'll repeat this again later when it becomes useful for us. The sum of the probabilities of every possible outcome is 1. So if I go through with my die, I say, okay, what's the probability of rolling a 1 plus what's the probability of rolling a 2 plus the probability of rolling a 3? If I add up the probabilities of all possible outcomes, it's 1. Okay, so the sum of the probabilities of all possible outcomes is 1. Okay, there's probability trivia. Yo.
So, how is it that sometimes they're able to say, like, for example, at my job, my boss was like, well, last year there was a 190% turnover rate versus now we're at 120%. Is it, how come at that point it's not out of 100?
Okay, so what you're talking about there, so the question, in case you hear it or on the, is sometimes people will say that a rate is 150% or something like that, right? Is what you're saying. So you're talking about a rate, which is different than a probability. And so when you say something's at 150%, well, you would say like 100% is full capacity, right? So 100%, 150% means you're above capacity. Or if you're talking about the rate of change of something, if something has changed by 150%, this is something we cover in the MGF 1107, but the percent increase or percent decrease of something. So this is a little off topic, but I want to answer the question. The percent change is you take the original amount. So if you're looking from year to year, right? So if you're looking at what happened on a date in 2020 versus what happened on 2021, you would say the original amount, which would be the 220, minus the new amount. No, sorry, I got it backwards. Sorry, everybody. The new amount minus the original amount, that's better, divided by the original. And this will give you like the percent change in something. So when somebody's saying that something's changed by 190%, that means that the new amount is way bigger than the original amount. So if you were thinking about your salary, you know, and you got a raise, and it'd be nice to get 190% raise, so I can pray about that. Because if your percent change is 100%, that's doubling something. So anyway, hopefully that brief explanation tells you why. But as far as probability is concerned, okay, so we're not talking about a rate, okay, we're not talking about a change. As far as probability is concerned, it will never be outside of 0 to 1. All right, so just some problems that we're going to go ahead and do. What I'm gonna do is I'm gonna summarize the structure of a deck of cards for you, because a lot of your problems will be on the deck of cards. You don't have to worry on the test. I will put a picture of the deck of cards up because that is not prerequisite knowledge for this class. Okay, but the reason that in probability we use the deck of cards to try to learn about probability is it's interesting enough that there's lots of different problems you can ask, but it's not such a large number that it's cumbersome to work with. Okay, so in a standard deck of cards, okay, so if you've played anything, Dad likes to play cribbage, so I learned that recently, but outside of that, I haven't played cards since I was in college, but we used to play hearts all the time, so I don't know if anybody plays hearts, if that's still a thing. I know phones. We didn't have phones back then. We had to light fire and all that sort of stuff. Okay, standard deck of cards. In a deck of cards, there are 52 cards. Yeah, me and my mom when I was a kid, we used to play Go Fish. Yes, thank you for the memories. I appreciate it. Yes. Oh, and my mom also liked to play War, where you'd divide the deck in half, and then you'd flip over a card, and then whoever had the higher card, you win the war. And then if you tie, then you lay down a bunch of cards and you flip.
There's no skill involved at all.
No skill at all. It's just a way to pass time. And then so again, when I was a kid, sorry, all of you watching this on video. This has been a little bit of a weird day for all of us. Okay, so when I was a kid, we didn't have video games, we didn't have anything. So yeah, we played cards and we built puzzles and we ran around outside and I don't know, it seemed okay. So anyway, no more stories. We're recording this. Okay, there's 52 cards in a deck of cards. And the way it breaks down in this, and this is why we use the deck, because there's some symmetry to it, but there's enough interesting little things. There's 52 cards, 26 of the cards are red, and then 26 of the cards are black. Okay, so we can ask questions about the colors of different cards. For red cards, there's two what's called suits. Again, you don't have to know any of this when you're doing your homework problems. I believe they give you a picture. If they don't, just Google deck of cards, and there's lots of pictures. On the test, I will give you this. You do not have to memorize the deck of cards. For the red suits, there's a suit called the hearts. They have a little picture of a heart on them, and then there's the diamonds. They have a diamond on them. The black suits are the clubs, which for whatever reason, the club looks like a clover with a little foot on it. And then the spades, which looks like a heart. That's terrible. Paula, you want to come help me? I know you can draw. Okay, it looks like a heart that's been impaled right there. So there you go. And so again, there's symmetry. So because there's 26 red cards and they're divided into two suits, how many hearts, how many diamonds do you think there are? There's 13. Yes, there's 13 hearts. I'm just going to put in parentheses here. And there's 13 diamonds, and there's 13 clubs, and there's 13 spades. And then for each of the suits, each of the 13 cards, this is how they are labeled. Okay, they are labeled, they start with the ace. Okay, we're going to, in this class, if you are familiar with playing cards, if you love you some blackjack or something, we're going to consider ace low just to keep things simple. Okay, ace is going to be the same thing as 1. Okay, so no arguments. That's the way it is. It's my class, my rules. And then 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the last 3 cards are called face cards or picture cards. They're the royalty cards. There's one called the Jack. And then there's one called the Queen. Yes. And then there's one called the King. And I'm just going to put a little parenthesis here. That these are called the face cards or the picture cards. Outside of that, I'm not going to ask you any other trivia about dex cards. You don't have to know how many suicide jacks or suicide kings. I don't even know why there would be such a thing, but that's the way it is. The reason I wrote this on the board is just for people watching on video. I don't have the ability to share my screen and record what we do on the board at the same time. So I just wanted to summarize it. So given all that information, here we go. All right, I'm going to do this first one. If I have to pull a card randomly from the deck of cards, I want to know what's the probability that I pull a king out of the deck. So here we go. How many kings are there in the deck of cards? 4. There's a king of spades, king of clubs, king of diamonds, king of hearts. That's the way the cards work if you're not fully understanding. There are 4. How many cards total are there out of the deck of cards? 52. Now you can reduce that if you want. 4 out of 52 will reduce to 1 out of 13. But I'm guessing as you go through, it's going to be more common just to throw this down into the calculator. But again, remember, read what My Math Lab wants. Read how many places they want you to round to. I don't want you to accidentally miss a problem. So I'm just going to round this to the 4th decimal place just to get some good accuracy. 0.0769 or 7.69% of the time you're going to pull a king out of the deck of cards when you do that. So here's another one for you. This is your time to shine. I want to know what the probability that you pick a number less than 4. Yes, ace counts as one in our reckoning here. Okay, that's not, I understand that's not how it operates in games, but that's how we are doing it right there. Okay, so a number less than 4. So first off, what are the cards that are less than 4? They are the ace, the 2, and the 3. So there's 3 cards in each suit. Then there's 4 suits. So how many cards total is that are going to be less than 4? 12. Okay. 12 out of 52. Again, you can reduce that if you feel like it. I'm going to go ahead and just pop that in the calculator and round to the 4th decimal place just because I'm feeling like 4, so it's going to be 0.2308. Okay, is the probability that happens. Find the probability of selecting an even numbered card. Okay, what's the probability of an even numbered card? Yo. Nope, they're letters. On the card, it'd be a J, a Q, or a K, so there'd be no numbers. If again, for our reckoning, the reason I asked even is I didn't want to confuse anyone, but we're just going to count ace as 1 in these problems. Okay, so we'll count it as an odd number and all that. How many even cards are there in the deck? Okay, that is true. Just in case you don't see where we got 20 from, there's the 2, the 4, the 6, the 8, the 10. That is 5 cards out of the 13. So 5, but then I have 4 suits. So 5 times 4 is 20. So there's 20 of them out of 52. Again, you can reduce that by a factor of 4. That would work. I'm going to go ahead and divide. 20 divided by 52 is 0.3846. Yeah, I just felt spicy. Again, just follow whatever instructions you're given. Okay, I'm pretty sure my math lab will either ask for 3 or 4. I don't remember exactly. Let's do one more. Let's do the probability of the ace of hearts. What's the probability that you select the ace of hearts when you randomly select from the deck of cards? Sorry, swallowed wrong. Not sick. It's funny, you got to justify now, right? All right, ace of hearts. How many ace of hearts are there in the deck of cards? 1 out of 52. Indeed, that's a reduced fraction. You could leave it just like that. You don't have to do anything else. So just remember, if you're going to leave things as fractions, that is perfectly fine. Just make sure they're reduced if you're leaving as fractions. So this is 0.0192. We got the gist? We doing okay so far? Questions, comments, concerns? Okay. Just a couple more examples then, and we'll be good. All right, so here is another example. Let's say this, you're at a party and there's a cooler full of drinks. And let's say that we know that our hosts, they have 60 drinks in a cooler. And we're going to just assume they're all 12-ounce cans. Okay, so that way you can't distinguish one from the other. Okay, so there's 60 drinks in a cooler, and I know the following. I know that there are 20 Cokes. I know that there's 15 Sprites. I know that there's 10 Diet Cokes. So it's 20, that's 35, that's 45. Right now, 20, 35, that's 45, okay, and then we're gonna do, there's going to be 8 Dr. Peppers. I don't know why that just occurred to me. And then let's do, should have probably made this up before, but that's okay. You love me anyway. We're gonna go 5, we'll go 5 cans of, let's say, Yoo-hoo. Yeah, I know, last from the past right there, 20, 35, 45, 50, and then there's 2 beers, if you get lucky. There we go. You've never had a Yoo-hoo?
I have not.
It's basically just watered down chocolate milk,
Yeah.
is all it is. It's nothing super special. So, anyway, so I didn't know Yoo-hoo was gonna be so controversial. Picked it sooner, I guess. Okay, so here you go. This, we reach our hand in the cooler, we're not looking, or we just want to know what do we pull out. So here you go. I want to know what's the probability that you pull out a can of Coke. Okay, how many Cokes are there in the cooler? Out of how many total drinks? All right, and I'm just going to reduce that becomes 1/3 or 0.3333. If you reduce that, okay, let's ask this. What's the probability that I get a Sprite or Dr. Pepper? I want one of those sugary drinks. Yo.
Diet Pepsi guy, do you like Diet Coke at all?
Oh yeah, I'll drink it. I'll drink it when they're out of Diet Pepsi at the fountain. I'll fulfill my need with a Diet Coke. Yes. We'll just drink none of it, but that's okay. Okay, so how many Sprites or Dr. Peppers are there in the cooler? Okay, there's 23 out of 60. You can leave it like that. That's a reduced fraction, but if you made a decimal to, I'm just going to go to 4. If you did 3, that's fine. I haven't really given you any instruction. It's 0.3833. Okay, so since pretty much everybody in here, if not, I think everybody, I don't know, I don't predict these sorts of things, but hey, you're not 21 yet, so what's the probability that you don't pick the beer? Okay, I don't want anybody get me arrested at our picnic we're having. What's that? I'm 21. I put the beers in there for me. Okay, so the rest of you, you get Yoo-hoo and soda. How many not beers are there in the cooler? A lot. 58. I mean, the easy way to figure that out is there are 2 beers out of 60, so then everything else is not beer. So that's 60 minus 2 is 58 out of 60. Again, you can reduce that. It'll reduce to 29 out of 30. Or you can go ahead and give our decimal, and it's 0.9667. All right, we're doing all right. I've got one more example for us, and then we're done for the day. Any questions, comments, concerns that you have about probability calculating it? Okay, the last thing is there's a relationship between probability and if we have a figure, the amount of area something takes. So for instance, let's say you're playing some sort of board game, which you guys probably don't because you didn't even know what a deck of cards were. So it's okay, no judgment. Okay, so here's the spinner on my board game, and I'm just going to, let's do this. I'm going to divide this up into 8 spaces. Not too bad. I'm just gonna put in parentheses here, just assume that all the spaces are equal sizes. Otherwise, this gets more complicated and we're not ready for that yet. And since I only have 3 colors of pens, okay, we're going to, here's a red space. There's a red space right here. And hey, we'll put another one right here, right next to it. There we go. We'll do 3 red spaces. We're going to do a green one right here, a green one right here. And I know you don't have different inks, so you might just write the letter G for green or something, not trying to exacerbate you. And then we'll do 4 green spaces, and then, so let's pretend this is the spinner. We're playing Candyland. Anybody ever play Candyland? Okay, that's good. You all know what the candy is. Okay, so here we go. So because all the spaces are the same size, okay, we can just calculate our probability in the same way. Yeah.
Does that work for anything?
Yes. In fact, one of the homework problems, you're going to be given like a dartboard. It's actually, I think it's the last problem. Make sure you do it. It's a good problem. If you're, I'm sure we might have a question on it. Love to do the question. Okay, but I want to make sure. So my spaces are equally sized. So here's what I want to know. What's the probability that I go ahead and spin and I get a green space? Okay, so you calculate that first, then we can shout it out and have a good time.
You don't use a spinner to get rid of that, right?
It's been a long time for me.
I don't know, I can't remember.
I'm gonna
Okay,
be
like,
50
like
years
has a
old.
spinner.
Life, yes, life has a spinner. Life has that weird spinner that if you spin it hard enough, it'll fly. It's great. That was actually more fun than the game. That and driving the car over the hills, like that's what I
They have
enjoyed.
pets in it now.
All right, the probability that's green. Okay, when I spin the spinner, how many green spaces are there?
Oh, well, there's 4 green, but there's 8.
Thank you, because I was wondering what spinner you were looking at. I'm glad we got that settled. Okay, 4 out of 8. So you would expect half the time that you're going to get a green space. What's the probability? Finish this up. Then what's the probability of red? And then what's the probability of blue? Just give you a moment to finish that up. Okay, so the red, how many red spaces are there? 3 out of 8. Okay, we'll leave it 3 out of 8. How many blue spaces are there? 1 out of 8. Great. That's the probability. Just to validate something I said earlier, one of the trivias about probability told you that when we add up the probabilities of every possible outcome, it should be 1. Let's just make sure that happens because there's no other spaces aside from red, blue, or green. So 4 out of 8 plus 3 out of 8 is 7 out of 8. Plus 1 more, that's 8 out of 8. That's 1. That's every possible thing that can happen. When I add up those probabilities, I get 1. 1 means everything that can happen.